So today's topic, we're going to continue our discussion of functions. And we're going to get a little bit more specific with defining domains, ranges, and the vertical line test. Let me go ahead and refocus the camera there. Let's see if we can get that a little sharper. There we go. So let's go ahead and make these definitions. I think I mentioned these last week. So to formally write it down, the domain of a function is the set of all possible inputs. I.e., possible values of the independent variable. And then likewise, the range of a function is the set of all possible outputs, i.e., possible values of the dependent variable. And we defined what a function was last week. And recall we said that the relationship between two variables, one we call the independent variable, the other the dependent variable, such that for every input, for every value of the independent variable, there is exactly one value of the dependent variable. So we can write that now in terms of this language of domain and range, a function. So I'll abbreviate function FNCT is such that for every value in the domain, there's exactly one value in the range. Examples. Analytically or formulaically, anytime we can solve for y, it defines a function. So if we have y on one side of an equation, all x's on the other side, automatically defines a function. Why is that? Well, that's because no matter what x value we plug in, how many y values do we get? Exactly one. And this is assuming we're writing y specifically as a function of x. So for any x value we plug in to any of these, we perform the indicated operations, and then we will get that one specific y value. in the range. Things that are not functions in general, if you cannot solve for y, it has a strong possibility that it is not a function. It still can be. There are certain situations where we might have complicated expressions like y times natural log of y, where we cannot necessarily solve for y in terms of x as a specific formula, but by the defining property of a function, it's still satisfied. But a good indicator of when something is not a function is this possibility of not being able to solve for y. So what do you have to check? If we have things like x equals y squared, this does not define y as a function of x, because we can have multiple y values that correspond to a given x value. So for example, when x is equal to 4, we could have y be negative or positive 2. So we would have two values in the range for only one value in the domain. So this isn't going to be a function. Likewise, we will see things like x squared plus y squared equals 1. That gives us a circle. And a circle, as we will see later, of course, will fail the vertical line test and will not be a function. But likewise, we could just pick points for x and then figure out, well, if there's two separate y values that correspond to, say, when x is 0, then it's not going to be a function. For tables, we wanted to ask ourselves, when is y a function of x, given the information in the table? One easy rule is that if the x values are only listed once, always a function. So no matter what y values we have, it's still a function. Our function rule is not broken, because for every x value, there is exactly one y value. We can hit y values twice. We hit the y value of 2 at two different spots, but those correspond to two different x values. So we're fine. The information in a table will not be a function if you have x values listed twice and for those different, or for that same x value, we have different y values. So here this says that the x value of -1 should have y values of both 3 and 0. And this breaks our rule that I have two values then that would be in the range for a single value in the domain. Do be careful. I guess one more note on that. Sometimes there are tables, might be listed in a problem, where we can list an x value twice, but if I list the same y value for that, it can still be a function, right? All I did was list the point -1,3 twice. So this is still a function. Graphically, what's going on? Well, if we take a look at something that we solve for y, let's say y equals x squared. When we draw the graph, we already know it's a function because I can solve for y. And we can see the function property graphically by saying, well, wherever I have an x value, if I look at the y values corresponding to that, there's only one. So for this x value of 3 here, we would have a y value of 9. What's going wrong with things that aren't a function? So if we look at x equals y squared, this is going to look like a parabola, but turned sideways. And as we saw in our numerical examples, when x is 4, there's 2 different y values, plus 2 and minus 2. And so our function property says that if a relationship is a function, then for any given x value, I can only have one y value. Graphically, we can deduce this by what is called the vertical line test. And we notice that for any given x value, if I draw a vertical line, there's a lot of different points that cross the graph twice, in which case that's not going to be a function. So let's write this down formally. So the graph of a curve defines y as a function of x if for any vertical line drawn, and we can say specifically at an x value in the domain, the line crosses the curve exactly once. And we see here, if it crosses more than once, that tells us that it is not a function. So here we have a lot of different points. We're drawing vertical lines at those specific x values will result in those lines crossing the graph more than once. Conversely, when we look at something that we know is a function, y equals x squared, no matter which x value we choose to draw our vertical lines at, those vertical lines will only cross the graph once. So that gives us a function. One thing to note is that if you have curves that pass the vertical line test at some values but fail it at others is still a failure. So something like this, I can draw vertical lines over here and that crosses only once. But as soon as I get over here in this small little region here, I can draw vertical lines, and now we're crossing 3 or 2 times. So if any of the vertical lines fail, it fails universally. It's not a function. The other thing to mention is that sometimes our functions can be discontinuous. So one way you can kind of think about it, if you're doing this online and you're given, say, a multiple choice, here's a bunch of different graphs, select which one's a function or select which one's not a function. One thing you can kind of do is on your screen, well, if you trace your finger from left to right, you should be able to start from the left and go all the way to the right without stopping and going back. So it's only starting from the left and going from the right, but you might have to lift your pencil to go up or down. So we can see on this one, if I start from the left and trace the curve, I have to stop and then I'm going back to the left and then now back to the right. Not going to be a function. Likewise, this guy, I'm going to the left, stop, and then I'm going back to the right. Not a function. However, if we have a graph, let's say it can still even be discontinuous, that I start on the left and I draw and I come up and I go all the way up here, and then I stop, but I only go straight down, and maybe I put a point, and I'm still going up and down, and then I'm still moving to the right. And drawing something like that. Still going to be a function. And again, we can check that with our vertical lines. This is defined everywhere. And no matter where I draw a vertical line, even if I draw a vertical line on top of this asymptote, it's only crossing at that one point. Whereas any of these other vertical lines only crossing the graph at exactly one point. So still a function. This is what we call a discontinuous function. And we'll work more with those in the coming weeks. Any questions on any of that? Okay, so the last thing I wanted to talk about today is, well, let's jump back into the domain. And specifically, how do we find domains of functions? We'll start off with the easy examples. Tables are easy. If we have a relationship given in a table, such that the table defines a function, x values are only listed once, automatically a function, then the domain is pretty easy. We simply list the set of x values, in which case set notation would be best for this, because it's only a finite set. We just list them all with commas in between squiggle brackets. That's all there is to it for tables. You're only given a small portion of the data, and so your domain is only the x values you have. Graphically, how do you determine a domain? Well, you can just essentially look at it. say we have a graph and it looks like a semicircle. Here, what is our domain? It's the set of possible x values. Well, where do I have x values defined that have a corresponding y value? It would be -2 to 2. So you could set this up in set notation if you prefer. Or in interval notation. Likewise, the range well, now it's the set of possible y values. So if we're looking at the curve, what y values do we hit? The smallest y value is 0 up to 2. Or you can write this in set notation if you prefer. Less than or equal to y. And sorry, I need to change that x. It should be a set of y values in R, such that y is between 0 to 2.
I have a question.
Yeah.
Why is it 0 to 2 and not 0 to 3?
Did I miscount? It is 0 to 3. Sorry. I meant to draw this as a semicircle, but I drew an extra tick mark. You are right. Let's make it 0 to 3. So not quite a semicircle then. It's like a semi-ellipse. The other thing we can see is, so for the sake of doing an asymptote example, so we have a graph that does this, but I don't have a point anywhere on this asymptote. How do we write that? And usually there's arrows to indicate that. If the function keeps going, if there's arrows, we kind of imply that it goes off to positive and negative infinity, at least for our domain on the x-bounds. So our domain's going to start at minus infinity. It's going to go all the way up to -1, but not hit -1. And then it's going to start immediately after -1 and go off to infinity. So you have to write it as a union of two separate intervals. Set notation for these is a little bit easier, because in this case, we simply have all real numbers, except where x cannot be -1. So for most of the homework assignments, I believe they want you to write things in interval notation. I don't know about written homeworks. Written homeworks, I think set notation is fine, but I believe on most of the web assigns and on most of the quizzes, domains and multiple choice quizzes will likely be written in interval notation. Okay, so well, that's tables and graphs. Pretty easy examples. Graphs we can just read off. Tables we can essentially just read off the domain. The harder part is what happens when I give a function analytically, when I give a formula for a function. So general rule. So if it is not specified, the domain of a function is all real numbers except where a mathematical operation doesn't make sense. So we'll see a little bit more about what I mean by if it is not specified. This will come up in piecewise functions, where piecewise functions in some sense are kind of just a collection of functions that we stick together. And on each piece, we specify a specific domain. Because I can always shrink the domain of a function and say, well, I only want to look at the function on specific values. But most of the times when we see a function, we just assume it's as big of a domain as we can have. And where can we not have the domain? Well, there's going to be some sort of mathematical operation that doesn't make sense. And in which point, we'll have to throw those values out of the domain. So what operations don't make sense? At the moment, you guys only need to know two. We cannot divide by a negative number. Or excuse me, cannot divide by 0. And we cannot take the square root of a negative number. Those are the only two you need to know at the moment. We will have other domain restrictions once we get into logarithms and once we get into inverse trig functions and trig functions in general. But that will be much later in the semester. For now, hopefully everyone knows those two from last Monday's material, from the material of just basic algebra. Okay, so let's do some examples. So if I'm not dividing by anything that could potentially be 0, and specifically if I don't have any x's in the denominator, then we're not going to divide by 0. And if there's no square roots, then what could mathematically go wrong with something like that? Nothing. So quadratics, linear functions, and in general, any polynomial there's nothing that can go wrong mathematically in performing those mathematical computations for any x value that I plug in. So our domain is all real numbers. And we'll talk more about how to handle those and find roots and specifically formally define what a polynomial is. Likewise, we'll do the same with these other functions. But for now, just know that if we give you a formula where, let's say, a division is involved, well, now there's a division and we know we cannot divide by 0. So how do we determine the domain? The way I like to do it is, well, we pick one of these rules, and in this case, the division rule applies. There's no square roots involved. And since we cannot divide by 0, the denominator cannot be 0. And how do we write that as a mathematical sentence? Well, the denominator is 5x, 5 plus x, and it cannot be equal to 0. you can treat these cannot equal to signs or not equal to signs exactly like equal to signs. And so if 5 plus x cannot be 0, when we subtract that 5, that tells us that x cannot be equal to negative 5. And this is the equation or the not equation that defines our domain. If we wanted to write it in set notation, it's fairly easy from here. Of course, the first part of set notation, it's usually just all x and r such that, and what is our property? X cannot be negative 5. Interval notation, we've got minus infinity up to negative 5, not including negative 5, but then immediately after negative 5 and all the way up to infinity, we can include. To do one with a square root, these can get tricky when there are complicated functions underneath the square root. And we'll talk more about this and see examples once we get into quadratic functions and harder rational functions, or perhaps even Wednesday. But for now, let's say we have a linear function. Let's do something fairly simple. Let's say 2x minus 6. But if all of that is underneath a square root, well, I now have some operations that we got to be careful about, right? Our function says take a number, multiply by 2, subtract 6, and then take a square root of all that. And so it's that square root operation, that last operation we perform, that could be a problem because we cannot take a square root of a negative number. In other words, we must take square root of number bigger or equal to 0. In other words, what's this say as a mathematical sentence? It says everything underneath the square root has to be bigger or equal to 0. And this is our domain defining inequality. So we're forcing everything underneath the square root to be greater than 0. And now when we simply solve for x, we figure out where our domain is. Domain is going to be the set of all x such that x is bigger than 3. So our set notation, fairly easy with this. The nice thing about solving things this way is that it makes the set notation straightforward, just like when we had that not equals to, this sort of last step that we end up with when we're comparing x to a number is essentially the right side of our set notation for our domain. Interval notation, not too bad either. We can include 3 and then anything bigger than 3, so 3 to infinity. Any questions? Cool. So we'll get into some harder examples in the coming days. That's all I wanted to do for now because I wanted to give us a little bit of time. Looks like we only got 7 minutes to get into the in-class activity.